Hey, welcome back to Fat Mama Physics. In this video, we are going to continue with the topic of fields, but this time we're going to look at gravitational fields, which have a lot of interesting similarities as electric fields, but of course they have their stark differences as well. But we, in this video, are going to tackle something about orbits. And how does orbits, total energy, potential energy, kinetic energy of a satellite are related, or interestingly related in orbits. So, on the topic of fields, topic 10, I know it's jumping around a bit, but here we have an example 3 in which I might have to break it down. I'm going to do example 3 and 4 essentially together, but essentially this question is asking for a satellite's gravitational potential energy in orbit. It's also asking for its total energy, but it didn't ask for the kinetic energy. So I'm going to break this down into more steps. I've added a previous page here to kind of to do that. So I'm going to change this entire question, and well, not entire question, but basically the workflow. I believe this was a satellite on Earth. So imagine I have this satellite here. It is in orbit, and I want to find a couple of things about the satellite. I want to find its total energy, I want to find its potential energy, and kinetic energy. Or I should say potential, kinetic, then the total energy. So let's start off with the first question. I might have to scroll back and forth between the two, so sorry, we gotta bear with me a bit. We have a 2,500 kilogram satellite, which is, I'm gonna say that's small m. It is orbiting this much meters above the Earth's surface, so it's not exactly from the center of the Earth, it is above the Earth's surface. So there's something we have to worry about there. What is the gravitational potential energy of the satellite due to the gravitational force due to the Earth? Due to. Okay, so a couple of things. We should probably draw this. So this distance here is 3.7 times 10 to the 7, no, 6 and then 7. Okay, 3.6 and 0 times 10 to the power of 7 meters. We are not told this in this question, and not sure why it didn't tell us. You're not required to remember this, but the radius of the Earth is 6.38, I believe, times 10 to the power of 6 meters. And the other thing you are not required to remember is the mass of the Earth, which is 5.98 times 10 to the power of 24 kilograms. So that would be given to you in a question, or in your data booklet, if your data booklet would have that. So we're going to use all this information to find the gravitational potential energy of this satellite. So gravitational potential energy, we know that is equal to negative big G, big M, small m over R, which is the distance of separation from the center of one mass to the center of the other, center of gravity of their other mass. So let's put in these numbers here. We know that one more thing. This little mass of this satellite, we know, wrong color, is 2,500 kilograms. So we have big G, we have the mass of the Earth, we have the mass of the small satellite, and this R is a combination of both this the height above the surface as well as the distance to the Earth's center, which is the radius. So we just have to be careful when substituting those numbers in. So that's going to give us negative 6.67 times 10 to the power negative 11, mass of the Earth, mass of the satellite, and last but not least, the distance, which is going to be, I'm going to have to add up the altitude, essentially, and the distance to the center of the Earth. And whether or not I get the right answer will tell me whether or not I've memorized some of these numbers correctly. Okay, I got 2.35, and don't forget that's negative 3529 times 10 to the power of 10 joules. So, how much did I remember? I got 10 to the power 10, and well, guess what? If we rounded his 2 sig figs, then I didn't do too bad. This 5 rounds to 3 up to negative 2.4 times 10 to the power of 10 joules. So there you go. There's the gravitational potential energy of the satellite. You might be thinking, why the negative sign? The negative sign is basically to set the reference point. In all of the calculations you've done before, we've essentially assumed that the surface of the Earth has a reference point of 0, in which we compare all of our potential energies to. But now, since the Earth is no longer the center, or no longer we care about it, we often will compare the gravitational potential energy to 0, where it is at infinity. So anywhere less infinity, we are going to have gravitational potential energy, which will be less compared to whatever object's at infinity, thus being negative. So the negative there is just as a placeholder for where the reference point is, okay? Not going to be, hopefully will not trip you over, because it has not a lot of significance. It is just the fact that we set a different reference point, okay? Okay, so the next part of this video, now that you know the gravitational potential energy, to find the total energy of the satellite, you know that the total energy of the satellite depends not only on the gravitational potential, but also as well on the kinetic energy of the satellite too. So this is important. When the satellite is moving, we know it has velocity. The velocity of the satellite is going to depend on where it is in orbit. And we know for a satellite that is in orbit, it will experience a gravitational force, in which this gravitational force will keep this satellite orbiting in circular motion. Otherwise, it will go out of this orbit, or it will crash land on Earth. It's a sweet spot. So that gravitational force acting on a satellite is going to determine how fast it will move in relation to where the planet is. Okay, so let's use purple. Alright, so this object, to find the kinetic energy, we need to know the speed of this object. So how do we find speed? We have to look at circular motion. If we look at circular motion, then we know that the net force acting on the satellite is the Newton's universal law of gravitation, Fg, which is big G, big M, small m over r squared. R being the distance of separation from the centers to the centers. And that is going to be equal to the mass times centripetal acceleration of the satellite, in which we know that this is just mv squared over r. Okay? mv squared over r is essentially showing that this object is in circular motion. One unique case of Newton's second law. Here we know that a few things can cancel out. First of all, this mass here, but wait a minute. Do I want to cancel things out? This is actually pretty nice, because all I need here, I just need mv squared, because mv squared is part of kinetic energy, right? Since kinetic energy is just 1/2 mv squared. So if I just get this mv squared here, I just have to take half of it to give me my my kinetic energy. So why won't I rearrange a few things? First of all, let's get rid of this r, because we have 2 of those, okay? So that goes out of my way. And whoa, that was very convenient, because now we just have mv squared equals to big G, big M, small m over r. Hey! That's interesting. Doesn't that just look like the gravitational potential energy? We're not done yet, though. We still need to add the half to give us the kinetic energy. So let's put the half in, okay? And of course, if I multiply both sides by half, it doesn't change my equation. But hey, look! Now we have kinetic energy. This is kinetic energy. This is kinetic energy of the satellite. Kinetic energy of the satellite. Kinetic energy of the satellite. But hey, what? No way. So the kinetic energy of the satellite is just 1/2 big G, big M, small m over r. Whoa, dude, compare that with EP, with potential energy. That's just negative. But that's just the negative of big G, big M, small m over r. So that's interesting. So the kinetic energy is actually related to the potential energy in some ways. it's actually, wait, let's work it out. It's actually, if we take half of EP and get rid of that negative sign, if we just put a negative sign in front, that's essentially EK. Damn, that's pretty cool. Hey, and guess what? Since we know the kinetic energy, we know the potential energy, let's solve for the total energy. So total energy equals to the sum of all energies, of course, which will only be EK and EP in our case. EK is going to be 1/2, no, though, it's positive, not negative, minus, because EP is negative here, and since we subtract these two, we're actually going to end up with negative, and that's 1/2, so essentially you have 1/2 minus 1. 1/2 minus 1 is just going to be 1/2. And the rest of this is this big G, big M, small m over R. That is total energy. Woohoo! Look at that. So total energy is essentially the negative of EK. Whoa, that's interesting. Or in other words, the total energy is going to be 1/2 of the potential energy. Look at all these relationships. Whoa, that's so cool. I don't think that's available on your data booklet, so you better understand how to derive EK and total energy of a satellite in orbit. Note, only in orbit, okay? Okay, I think this video has gone on pretty long, and we haven't really solved the rest of the problem, but we now know how to find total potential energy. So let's go ahead. What is the total energy of the satellite in this last question? So let's go ahead to calculate the total energy. So total energy, now that we've shown this is 1/2 big G, big M, small m over R, we can do some substitutions here. So big G is just, woohoo, slow down there. 6.67 times 10 to the power of negative 11. Mass of the Earth, 9.8 times 10 to the power 24. The mass of the satellite is 2,500. Distance of separation is going to be the sum of the radius of the Earth plus the altitude, which is 3.6 times 10 to the power of 7. All of these in meters. So let's put this in the calculator. I guess we can always check if I have any mistakes here. So I get 1.176 times 10 to the power of 10 joules. And rounded up, this is 1.2 times 10 to the power of 10 joules. So if you take a look at this, the total energy, this is essentially half of this one on top. Oh, did I forget a negative? Yes, I forgot a negative. Okay, this is essentially half as the potential energy there above. So I didn't even have to calculate that. I could just took half of that, which is total just half of potential energy. But I did that just to double check my calculations there. So notice then you get all these interesting shortcuts when you understand how to derive all of these relationships. So on a multiple choice question, you can probably, if you know these relationships, you may be able to answer some multiple choice questions easier. If not, the multiple choice questions might assume you know what the relationship of potential energy, kinetic energy, and total energy. So that's it, folks, for this question. Sorry, I did it in the page above. In the next video, we are going to apply a different situation here. What happens if I want to move this satellite to a different orbit? How much work I need to do for that. So, more interesting stuff. Next question. Thank you for watching. Stay tuned. Family Physics signing out.